Welcome to Module 12. In this lesson we'll be looking at how the property tables were constructed and some of the diagrams that go along with these are an alternate way of presenting the data. We will in particular be focusing on looking at the pictures, but then also at the math behind those. So in this module, what we're going to learn to do is to recognize some of the most basic diagrams of thermodynamic properties. Now we've already looked at the PV and TV diagrams, but some of the other ones that are very common, especially historically, are the temperature versus entropy diagram, and then a family of diagrams called Mollier diagrams. A Mollier diagram is simply any diagram with one axis being enthalpy. The two that are most common that we'll be considering for pure substances are pressure versus enthalpy and enthalpy versus entropy. We're going to be looking at both how people would read values from these diagrams and then also relating mathematical models to these diagrams. So let's start by looking at the temperature versus entropy diagram. This is very significant because if we remember the Carnot cycle, it was 4 processes that connect together to create a cycle. And there were 2 isothermal steps and 2 adiabatic steps. And because they would be isothermal or adiabatic, that meant that on a TS diagram for reversible processes, this forms a perfect rectangle. And the work, the net work, would be the work, the net heat is the area inside this rectangle created here. The work is going to be related to the PV diagram, so sorry, I misspoke there. But anyway, so this is a very common diagram that people would consider because it's useful because if you get straight lines on these adiabats, okay, then you get something that's reversible. So it was a way to very easily recognize whether or not you had reversible processes. The Rankine cycle is going to, again, the ideal Rankine cycle is somewhat similar to the Carnot cycle, except that if we leave this 2-phase region, my heat transfer steps would go from being a compressed liquid to superheated vapor, and I might do my cooling from the superheated vapor state, but I'm more likely to start it as a saturated liquid vapor mixture, and I would cool it down to being a saturated liquid. But then I would go through the rest of the Rankine cycle, and the diagram for reversible looks something quite similar to this. So a TS diagram has been a way that we've been presenting cycles throughout all of your other thermodynamics courses. So what do these look like for some various substances? So I've just kind of randomly online chosen a couple of diagrams just to kind of make my point. So this is temperature versus entropy for oxygen. And so we have temperature on the vertical scale, the horizontal scale is entropy. And what you typically do is you have a region that's going to be carved out where you have 2 phases, and pressure and temperature are uniquely related along that in that region. And so you're going to find that if you look at a constant pressure, it's going to be straight across at a particular temperature, but it has a very strong entropy change as you go from saturated liquid to saturated vapor. But once you hit this gaseous state, the pressure will increase rapidly. So we end up with these, and each of these lines here is for a constant pressure. This is a very typical type of presentation of temperature versus entropy. So if you look at one of these, this is just kind of a generic one, you could draw your temperature versus entropy. Again, we have this region here where I have the 2 phases, saturated liquid over here, saturated vapor over here, they call it water, and dry steam. And then we have these lines of constant pressure that come straight across and then sweep up dramatically. We also could impose some lines where I traced constant volume. If I were to keep the volume constant and change temperature, what would happen to the entropy? And those will form some different curves. Or I could look at how temperature an entropy change if I hold the enthalpy constant, such as passing it through Joule-Thomson valve, something like that would hold the enthalpy constant. And so we have different kinds of curves that can be drawn on here. And so if I wanted to read a value off of these, I would find, say, my pressure, if I knew pressure. I'd find my volume, if that was what I knew. I would find my enthalpy, if I knew that. And a point along there for, say, the temperature could then be read straight down for the entropy. I could also find random intersections of these things. Where does this intersect with the constant enthalpy line? And I could find some other things by these. Now, one of the things that is going to be significant for us that I want us to start taking a look at is how do you go from one point to the next here? So if I had measured, say, a saturated vapor value at, let's go with this 1 bar line right here. And I wanted to know where the next point was, but I didn't have all of that superheated vapor data, then one thing that I can do is I can predict it. So the way to predict where that point should be is by looking at the slope. It points me in the direction of the next point. So the slope, well, I'm looking at, this is like my y-axis, and this is like my x-axis. So it's the change in temperature over the change in entropy. But I have all these different lines. So I have constant volume lines, I have constant pressure lines, I have constant enthalpy lines. So if this, for instance, is a constant volume line here, then it's how temperature changes with entropy while I hold the volume constant. This one is how temperature changes with entropy while I hold the enthalpy constant. This one right here would be how temperature changes with entropy while holding the pressure constant. Now, we know how to calculate these slopes here because we had that other work. So we've worked with fundamental relations and Maxwell's. So, for instance, if we wanted to know what the slope is for that constant enthalpy line, well, the slope is dt ds with constant h. When I have an energy down here, this is one of those times when I use the triple product rule because Maxwell relations and fundamental relations never hold an energy term constant. So the triple product rule gives me this result. This is okay, but everything I know is going to be like dH d something. So let's just reorder this by using the reciprocal here. So dH ds with constant temperature over dH dt at constant entropy. Then I'm going to try and simplify these. So I looked at one of them at a time. So let's look at the numerator, dH ds at constant temperature. Well, dH is equal to T ds minus V dP. So if I take the derivative with respect to S, ds ds is going to be 1, so I get T for the first term, minus V, and then dP ds at constant temperature. That is interesting, but I don't really know what that is. Whenever I see S in the expression, it's not going to be one of my measurable variables. So what I can do is I can use the Maxwell relations. So the Maxwell relation for dP ds at constant temperature is dt dV at constant pressure. All right, so let's look at the denominator, dH dt at constant entropy. Well, again, using TDS minus VdP, well, if I'm holding S constant, ds dt at constant S is going to be 0. So I'm left with just V dP dt at constant S. And this is the Maxwell that relates to that. That's somewhat unfortunate, okay, that has S in it. It's not something I know, but this had constant S in it, which is also something I don't know. So what I can do is with this form, I can use the chain rule. The chain rule is not the same as the triple product rule. Here I am changing what I'm holding constant. Here on the chain rule, I keep still holding P constant, but I insert the variable that I do know something about with S. And that's ds dt. So if I insert a t in the denominator, I need to insert a t in the numerator with the dv. So this is the chain rule. And ds dt at constant p, I know that as c sub p over t, and these are all measurable properties, so if I had an equation of state, I would be able to take those derivatives if needed. And so therefore the slope of this is going to be these in terms of measurable properties. Okay? So it seems like a lot of work, but if I have limited data and an equation of state, this is the way that I would be able to generate the entire curve.